All right, so at this point, we're basically going to put together everything we've been doing translationally and rotationally with Newton's second law to work what are known as static equilibrium problems. Now, many of you in this class will end up taking a course called statics that, of course, is basically nothing but static equilibrium problems. So what we're going to do is sort of set up what a static equilibrium problem is, and then the way that we're going to work it in 298. So hopefully you can have a good solid foundation when you have to take statics. So when is a body in static equilibrium? Well, there's basically two criteria that it needs to meet to be in static equilibrium. One is translational equilibrium. It says that the sum of all the forces, right? So the vector sum of all the forces acting on the object, they've got to all cancel out. So F net's got to be 0. We know that we live in a three-dimensional world, so in general, this gives us three equations. It says that the x component of all the forces have got to be 0 when you add them up. The y components of the sum of all the forces have got to add up to be 0, and the z component of the sums of the z components of all the forces have got to add up to be 0. Our second condition is rotational equilibrium. So rotational equilibrium says that when you add up all the torques acting on the object about some pivot, those also have to be 0. And again, since we live in a three-dimensional world, we could deal with three equations. So summing up the torques about an x-axis, a y-axis, and a z-axis. What we're going to do in this class to simplify problems is basically we're going to say, you know what, let's just focus on situations where we've got forces that act in the x and y, and that's going to give us torques that act in the z. So we're basically going to be able to draw all our forces in the plane of the page, and then we'll concentrate on torques that point into or out of the page. And so we'll set up these three equations in working a static equilibrium problem. So what's the process that we're going to do? Well, we'll start the same place we always do by drawing an extended free-body diagram. So that extended free-body diagram will let us show not just the forces that act on the object, but where they act. Then we'll pick a coordinate system, and here we're also going to need to pick a pivot point. So what's the point that we want to use to do our torque calculations from? Then we'll break up the forces into their x and y components, so we can go ahead and set up our two force equations. Then we'll come back and calculate, given our choice of pivot, calculate the magnitude and direction of each torque about the pivot for each force acting on the object. That'll let us set up our torque equation. So what we'll see is our choice of pivot's going to matter. And we'll talk about ways that we can make a most convenient choice to simplify what's going on in the problem in setting up our torque equation. At that point, we've got three equations. We'll have three unknowns. We'll go and solve for our unknowns. So this is, in some sense, this will be sort of the culmination of our Newton's second law problem, because we're going to deal with both translational motion and rotational motion. We are going to deal with static equilibrium, so we know that the sum of all those forces and torques has always got to add up to be 0.